Every detail in this story comes from real scientific research and observation. Something crossed the solar system in 2017. It did not slow down. It did not follow the rules. Astronomers pointed their instruments at a single point of light and found a shape no comet, no asteroid had ever shown before. 10 times longer than it was wide, tumbling end over end like a piece of wreckage thrown from somewhere else. No tail, no glowing halo of gas, and yet it accelerated, pushed forward by a force no one could fully explain. Its path bent through the inner solar system and never closed. It came from outside. It is leaving forever, and it will never return. One Harvard astrophysicist looked at the data and asked a question that made headlines around the world. Could this be technology? Others said no. The truth, they argued, was stranger and more ordinary at the same time. A red sun-scorched surface, a trajectory traced backward to the direction of a single bright star, a visit that lasted only weeks before the object vanished into the dark, beyond the reach of every telescope on Earth. For decades, scientists had calculated that objects from other star systems must occasionally pass through our own. The mathematics said it was only a matter of time. In October of 2017, the proof arrived, and it did not answer the old questions. It only opened new ones. A cigar of rock and ice, tumbling in silence, moving fast enough to escape the sun's gravity forever. No radio signal, no paint, no metal seams, nothing built by any hand, only a shape, a speed, and a mystery that professional astronomers are still arguing about today. This is the story of the first confirmed interstellar object ever observed by human instruments, what it was, what it almost certainly was not, and why, years later, the argument over its true nature has still not been settled. It came from another star, and for 11 days, it let us watch. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Everything you're about to hear is built on real observational data, published in peer-reviewed astronomical journals, and drawn from the actual measurements taken during those 11 days of observation. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. In October of 2017, a telescope on the summit of Haleakala on the island of Maui was completing its nightly survey of the sky. The telescope was called Pan-STARRS, short for Panoramic Survey Telescope and Rapid Response System, and its purpose was simple: to scan the sky repeatedly, night after night, searching for anything that moved against the fixed background of stars. Most of what it found were ordinary objects, asteroids and comets that belonged to our own solar system, following orbits that had been mapped and predicted for centuries. But on the night of October 19th, it found something that did not fit any known orbit at all. The object was faint, fast, and its path curved in a way that no bound object, nothing gravitationally tied to the sun, could ever curve. Within days, astronomers around the world understood they were looking at the first confirmed visitor from beyond our solar system. The scale of that moment is difficult to overstate. For a body to be considered interstellar, its trajectory must be hyperbolic, meaning its path is open rather than closed, an arc rather than an ellipse. Every planet, every asteroid, every comet native to our solar system moves in a closed loop around the sun, bound by gravity, returning again and again. An object on a hyperbolic path arrives once, swings around the sun under its gravitational pull, and departs, never to return. Astronomers had long predicted, on statistical grounds, that such objects should exist and should occasionally pass through the inner solar system. But prediction and observation are very different things, and for decades, none had ever been confirmed. This was the first. Credit for first flagging the object went to Robert Warwick, working with the Pan-STARRS survey team in Hawaii. Warwick noticed the unusual motion in the data and reported it to the Minor Planet Center, the international clearinghouse responsible for cataloging solar system objects. Within hours, other observatories around the world redirected their instruments toward the same coordinates, racing to gather as much data as possible before the object moved out of range. Speed mattered enormously here, because unlike a planet or a well-behaved asteroid, this object was not going to stay. It had already passed its closest approach to the sun days earlier, on September 9th, and by the time it was discovered, it was already moving away, accelerating outward, gaining distance with every hour. The early calculations were startling. Based on its brightness and its distance, astronomers estimated the object's size at somewhere between 100 and 800 meters along its longest axis, though the true dimensions would prove difficult to pin down precisely, for reasons that would only become clear as more data came in. Its orbital eccentricity, the mathematical measure of how elongated an orbit is, was calculated at approximately 1.2, a value that immediately told astronomers this was not a solar system object. A closed elliptical orbit has an eccentricity of less than 1. A perfect circle has an eccentricity of 0. Anything above 1 describes an open hyperbolic path, a trajectory a body follows exactly once. No comet, no asteroid ever discovered before had shown a number like that. Word spread through the astronomical community within days, not weeks. Telescopes at the European Southern Observatory in Chile, the William Herschel Telescope in the Canary Islands, and observatories across 4 continents turned toward the same point in the sky, working in coordination through the International Astronomical Union to gather spectra, brightness measurements, and precise positional data before the window closed. This kind of rapid global cooperation is rare in astronomy, reserved for events considered genuinely historic. Scientists understood almost immediately that they were watching something that might never be observed again in a human lifetime. 11 days, that was the entire window the world had to study it. The name eventually given to the object reflected the place of its discovery. Hawaiian language experts, consulted by the discovery team, proposed the word ʻOumuamua, which translates roughly to a messenger from afar arriving first, or more literally, a scout. The name captured something essential about the object's nature. It was the first of its kind ever confirmed, a lone traveler that had crossed unimaginable distances to pass, briefly, through a solar system it did not belong to, before continuing on a journey with no destination and no return. The naming process itself followed strict astronomical convention. The International Astronomical Union assigns official designations to newly discovered objects, and in this case, the object was first catalogued under a provisional designation before receiving both its permanent alphanumeric identifier, 1I/2017 and its Hawaiian name. The I in that designation stands for Interstellar, a new category of object that had never before been needed. Oumuamua became, by definition, the first member of an entirely new class of astronomical bodies. To understand why this classification mattered so much, it helps to consider the numbers involved. At its closest approach to Earth, Oumuamua passed at a distance of roughly 24 million kilometers, about 60 times the distance from the Earth to the Moon. It was moving, at that point, at a velocity of approximately 87.3 kilometers per second relative to the Sun. To put that speed in perspective, a rifle bullet travels at roughly 1 kilometer per second. Oumuamua was moving nearly 90 times faster than that, and it was doing so not because the Sun had accelerated it to some enormous speed, but largely because of the velocity it already carried when it arrived. The Sun's gravity bent its path and added some additional speed during the close approach. But the object's fundamental velocity, the speed it carried in from interstellar space, was already immense. That baseline speed told astronomers something important. If Oumuamua had originated somewhere within our own solar system, ejected from the outer regions by a gravitational encounter with a planet, its velocity relative to the Sun would have settled towards zero at a great distance, the natural behavior of anything gravitationally bound to our star. Instead, Oumuamua carried what astronomers call excess hyperbolic velocity, extra speed that could not be explained by anything happening within the solar system. That excess velocity was the fingerprint of an interstellar origin, and when astronomers traced the object's path backward through space, accounting for the Sun's gravity and the motion of nearby stars, the trajectory pointed toward the direction of the constellation Lyra, roughly in line with the bright star Vega. This did not mean Oumuamua came from the Vega system itself. Stars are not fixed in space. They drift over time, and Vega's position 25, 50, or 300,000 years ago, whenever Oumuamua might have been ejected from its home system, would have been different from where the star sits today. What the backward trajectory really told astronomers was a general direction, a rough heading, rather than a specific point of origin. The object could have been drifting through interstellar space for hundreds of thousands, even millions of years, ejected long ago from a planetary system somewhere in the direction of the constellation we call Lyra, tumbling silently through the vast emptiness between stars until by chance its path intersected with our own solar system. A journey with no beginning we can name and no end we will ever see. That single word, chance, sits at the center of everything remarkable about this discovery. The volume of interstellar space is staggeringly large, and the volume occupied by our solar system, even generously defined, is vanishingly small by comparison. For Oumuamua's path to intersect ours, and for that intersection to happen during the roughly 60 years humanity has possessed telescopes capable of detecting something so small and faint, required an alignment of probability that some astronomers described at the time as almost impossibly fortunate. And yet it happened. The statistics that predicted such objects must exist had finally been vindicated by a single fleeting observation. What made the object even more compelling was what came next. As more data arrived from observatories across the globe, Oumuamua's behavior began to raise questions that its origin story alone could not answer. Its shape, its color, and above all, a subtle but undeniable deviation from the path that gravity alone should have produced, would soon turn a straightforward discovery into one of the most debated objects in the history of modern astronomy. Before any of those deeper questions could be addressed, the astronomical community first had to complete a more basic task, confirming beyond doubt that the object's trajectory really was hyperbolic and not simply the result of a measurement error. In the earliest hours after discovery, this was not a certainty. Small telescopes and brief observation windows can introduce errors into orbital calculations, and astronomers are trained to be skeptical of extraordinary claims until the data has been checked and rechecked. Robert Warwick and his colleagues at the University of Hawaii's Institute for Astronomy spent the following days refining the object's orbital parameters, incorporating new positional measurements as they arrived from observatories in Chile, the Canary Islands, and elsewhere. Each new data point either supported or undermined the initial hyperbolic reading. By October 25th, 6 days after discovery, the evidence was no longer ambiguous. The eccentricity held steady near 1.2, the excess velocity remained, and the backward trace trajectory continued to point toward interstellar space rather than toward any known reservoir of solar system debris. This confirmation triggered something astronomers rarely experience, a genuine, unscripted moment of scientific history. Objects with catalog numbers are usually mundane, one of millions of asteroids tracked in the solar system's asteroid belt, differing from their neighbors only in minor details of size or composition. Oumuamua required an entirely new naming convention, a new interstellar object designation that had never before been used because no object had ever qualified for it. The Minor Planet Center, the Harvard-Smithsonian Center for Astrophysics Division, responsible for cataloging such discoveries, had to formally create a new class of object almost overnight. Somewhere, in an office humming with old servers and star charts, someone typed a designation that had never existed before. The public reaction, once news organizations picked up the story, was immediate and intense. Headlines around the world described the object using language far more dramatic than the astronomers themselves typically used, comparisons to interstellar probes, to messages from other worlds, language that reflected genuine public fascination more than scientific consensus. Professional astronomers, for their part, remained largely circumspect in these early days, treating Oumuamua as a fascinating natural object whose true nature would be determined by careful measurement, not speculation. That caution would prove important because the measurements that followed over the next several weeks would turn out to be stranger than almost anyone expected. One of the first priorities, once the orbit was confirmed, was determining the object's physical size and shape. This is normally a straightforward process. Astronomers measure how much sunlight an object reflects, combine that with its distance and its brightness as seen from Earth, and calculate an approximate diameter, assuming the object is roughly spherical, as most asteroids and comets are. But Oumuamua immediately broke this assumption. As the object tumbled through space, its brightness, as measured by telescopes tracking it night after night, did not stay constant. It varied dramatically, brightening and dimming by a factor of roughly 10 over the course of just a few hours, in a repeating pattern tied to its rotation. A brightness variation of that magnitude, from an object rotating on a roughly 8-hour cycle, told astronomers something remarkable. The object could not be anything close to spherical. A sphere reflects roughly the same amount of light, no matter which way it is oriented as it rotates. Only an object with an extremely elongated shape, far longer than it is wide, would show sunlight reflecting off a large surface area when its broadside faced Earth, and almost no light when only its narrow end was visible. Based on the extremes of this light curve, astronomers calculated an aspect ratio, The relationship between the object's length and its width of at least 6 to 1, and quite possibly as extreme as 10 to 1. No previously observed asteroid or comet in the solar system had ever displayed a shape anywhere close to that elongated. To visualize the scale involved, imagine an object roughly the length of a football field, but only as wide as a 2-lane road, tumbling end over end through space at nearly 90 kilometers per second. That comparison, while imperfect, captures something true about the object's proportions, even if the exact dimensions remained uncertain. Estimates for its longest axis ranged from roughly 100 meters to several hundred meters, with considerable uncertainty because the object's true reflectivity, how much of the sunlight hitting it actually bounced back toward Earth's telescopes, was never independently measured. A darker, more reflective surface would imply a larger object. A brighter, more reflective one would imply something smaller. Both possibilities remained on the table throughout the observation window. The color of the object added another layer to the puzzle. Spectroscopic measurements, which break down reflected sunlight into its component wavelengths, the way a prism splits white light into a rainbow, showed that Oumuamua's surface reflected more red light than blue light, giving it a distinctly reddish hue, similar to certain classes of asteroids found in the outer solar system, and to some comets that have spent long periods away from the sun's warmth. Astronomers interpreted this reddish coloring as evidence of a surface that had been exposed, for a very long time, to cosmic radiation. Over thousands or millions of years spent drifting through interstellar space, far from the shielding effect of a stellar wind, the surface of any solid object would gradually accumulate a crust of complex organic compounds formed as high-energy cosmic rays broke apart and rearranged simple molecules on the object's exterior. This kind of radiation processing produces exactly the kind of reddish coating spectroscopists observed on Oumuamua, and it fit naturally with the idea that the object had spent an immense stretch of time, far longer than the age of human civilization, traveling alone through the space between stars. A crust built one cosmic ray at a time over hundreds of thousands of years on a surface no eye had ever seen until that October. And yet, for all of this reddish, radiation-weathered exterior, one thing was conspicuously absent from every observation: any sign of a coma, the cloud of gas and dust that typically surrounds a comet as sunlight vaporizes ice near its surface. Comets, especially when they pass close to the sun, are expected to show this kind of activity, a visible tail or diffuse halo produced as frozen material sublimates directly from solid ice into gas. Despite Oumuamua's close pass by the sun, well within the orbit of Mercury, deep imaging by multiple observatories found no trace of a coma, no tail, nothing resembling the dusty envelope that typically betrays a comet's icy composition. Based on this absence, Oumuamua was initially classified as an asteroid, a solid, rocky, or metallic body, rather than an icy one. That classification, tidy as it seemed at the time, would not survive contact with the very next set of measurements, because while Oumuamua showed none of the visual signs of a comet, its motion through space told a very different story, one that would take astronomers by surprise and keep them arguing for years to come. As Oumuamua continued its outbound journey, moving farther from the sun and steadily fainter with each passing week, teams of astronomers continued tracking its position with extraordinary precision, using some of the most sensitive telescopes on Earth, including the Hubble Space Telescope, to squeeze out every remaining data point before the object became too faint to observe at all. It was this extended tracking, this refusal to let the object simply vanish into obscurity without a final, careful accounting, that revealed the anomaly. When astronomers modeled Oumuamua's expected path, using nothing but the gravitational influence of the Sun and the planets, a standard calculation performed routinely for every asteroid and comet ever tracked, the object's actual position, observed night after night, began to drift very slightly away from the predicted path. The discrepancy was small, measured in fractions of a percent, but it was consistent, growing steadily larger the longer astronomers tracked the object. Some small but persistent force beyond gravity alone, was pushing Oumuamua very gently off its expected course. For comets, this kind of behavior is not unusual at all. As ice near a comet's surface warms and turns directly to gas, that gas escapes in jets, and the recoil from those escaping jets acts like a very weak natural rocket engine, nudging the comet's trajectory in a measurable way. Astronomers call this non-gravitational acceleration, and it has been documented in comets for decades. The trouble in Oumuamua's case was that this exact kind of acceleration was showing up in an object that had displayed absolutely no visible sign of outgassing, no coma, no tail, nothing that should have been capable of producing the recoil force required to explain the deviation. This contradiction, a comet-like acceleration paired with an asteroid-like appearance, became the central mystery of Oumuamua's brief visit to our solar system, and it is where the next chapter of this story begins. The magnitude of the unexplained acceleration was, on its own terms, extremely small. Measured against the enormous distances and speeds involved in Oumuamua's journey, the extra push amounted to roughly a few 10,000ths of a percent of the sun's gravitational pull, acting on the object as it moved outward. In absolute terms, this worked out to an additional acceleration on the order of a few times 10 to the -4th centimeters per second squared, a number so small it would be utterly undetectable in almost any circumstance. What made it significant was not its size, but its consistency. The deviation appeared repeatedly across multiple independent observation sessions using different telescopes operated by different research teams, and it grew in a way that closely matched the pattern astronomers expect from a very specific physical process: acceleration that weakens in proportion to the square of the object's distance from the sun. That particular pattern, weakening with the square of solar distance, is the signature of sunlight itself doing the pushing, whether through direct radiation pressure or through gas released as sunlight heats a surface. Radiation pressure, the physical force exerted by photons striking a surface, was one of the first explanations astronomers tested. Every object in sunlight experiences a tiny outward push from the pressure of light itself, but for a solid rocky body of Oumuamua's estimated mass, this force is far too weak to account for the measured deviation, unless the object were extraordinarily thin and lightweight for its size, more like a sheet than a solid chunk of rock. This possibility, while intriguing, could not be confirmed or ruled out using the data available, and it would later become central to one of the more provocative interpretations of the object's nature. The more conventional explanation, and the one favored by the majority of the astronomical community, was outgassing, the release of vaporized ice from the object's surface, producing thrust in the same way it does for ordinary comets, but in a form too faint or too unusual to have been detected by the instruments watching for it. Standard cometary comas are made primarily of water vapor and dust, both of which reflect and scatter sunlight in ways that produce a visible glow. If Oumuamua's surface ice were composed of something else, something that sublimates, turns from solid to gas, without producing that same visible signature, it could theoretically explain both the acceleration and the absence of a detectable coma at the same time. Several candidate materials were proposed over the years that followed: carbon monoxide and carbon dioxide ice, both of which sublimate more readily than water ice and can escape without producing large amounts of visible dust, were early suggestions, though later analysis of the acceleration data suggested that neither of these compounds alone could account for the specific way Oumuamua's speed changed as it moved away from the sun. Water ice, deeply buried beneath an insulating crust of the reddish, radiation-processed material observed spectroscopically, was another candidate, though this too struggled to fully match the timing and strength of the observed deviation. Something was pushing it, and for years, no explanation fit every piece of the evidence at once. In 2021, a team of researchers proposed a specific and, for a time, compelling alternative: that Oumuamua's surface contained pockets of frozen molecular hydrogen, formed within an interstellar cloud of gas and dust long before the object was ever exposed to a star's warmth. According to this hypothesis, as Oumuamua approached the sun and its surface began to warm, hydrogen ice trapped within its structure could have sublimated directly, escaping in a form largely invisible to Earth-based telescopes, since hydrogen gas does not reflect sunlight the way water vapor or dust does. This hydrogen outgassing, the researchers calculated, could plausibly produce exactly the kind of non-gravitational acceleration that had been measured, without producing any of the visible signs that would normally accompany cometary activity. The hydrogen ice hypothesis was elegant, but it came with its own significant difficulty. Molecular hydrogen ice is only stable at extremely low temperatures, far colder than the environment Oumuamua would have experienced during even a relatively brief passage through interstellar space, if it had spent a long period exposed to the warming, however faint, of the galaxy's ambient starlight and cosmic background radiation. Critics of the hypothesis pointed out that maintaining hydrogen ice over the timescales required potentially hundreds of thousands or millions of years of interstellar travel, presented serious thermodynamic challenges that the proposal did not fully resolve. The debate over whether hydrogen ice could realistically have survived intact long enough to explain Oumuamua's behavior continued in the scientific literature for years after the object itself had become undetectable. Each of these hypotheses, carbon-based ices, buried water ice, molecular hydrogen, shared a common thread. All of them attempted to explain Oumuamua's unusual acceleration using purely natural, if unusual, physical processes, extending known cometary behavior into a regime that had simply never been observed before, because no interstellar object had ever been available to observe. This is essentially how planetary science normally advances. An anomalous observation forces researchers to extend or revise existing physical models, testing each proposed mechanism against the available data until one either fits convincingly or the search for a better explanation continues. What made Oumuamua different from a routine scientific puzzle was the sheer combination of extremes involved. An object with an aspect ratio unlike anything previously cataloged, a trajectory confirming, for the first time, that interstellar objects really do pass through our solar system. A color and surface chemistry consistent with an immense age and an origin far beyond our sun's influence, and an acceleration that mimicked cometary outgassing while showing none of the visual evidence that outgassing should have produced. No single previous observation of any solar system object had ever combined so many unresolved anomalies within a single brief encounter, observed for barely more than 2 weeks before the object slipped permanently beyond the reach of even the most powerful telescopes on Earth. By the time Oumuamua's light had faded past the detection threshold of the world's most sensitive instruments, in early 2018, astronomers had gathered an unusually rich data set for an object observed for such a short period. Precise measurements of its brightness, its color, its rotation, its changing position, and its subtle deviation from a purely gravitational path. And yet, despite that wealth of data, the fundamental question, what Oumuamua actually was, remained open. The object itself was gone, moving outward at nearly its original interstellar velocity, destined never to return to any star system, carrying its unresolved mystery with it into the dark between the stars. It was into this gap, this rare situation where careful, rigorous measurement had ruled out easy answers without providing a fully satisfying replacement, that some of the most striking and controversial proposals in modern astronomy would soon be offered, proposals that would move the conversation about Oumuamua from observatories and academic journals into newspapers, television broadcasts, and public debate around the world. Long before Oumuamua was ever detected, theoretical astronomers had already done the math on how many interstellar objects should be drifting through the galaxy, and how often one might be expected to pass close enough to our Sun for a telescope on Earth to notice it. These calculations relied on a simple but powerful idea. If even a small fraction of the material left over from the formation of other star systems is ejected into interstellar space, over the roughly 13 billion years the galaxy has existed, and multiplied across the hundreds of billions of stars the Milky Way contains, the total population of interstellar wanderers should be immense. Planetary formation itself provides the mechanism for this ejection. When a star system is young, surrounded by a disk of gas and dust, gradually clumping into planets, gravitational interactions between forming planets and smaller bodies, planetesimals, comets, and asteroids, routinely fling a fraction of that material outward at velocities exceeding the star's escape speed. Our own solar system almost certainly did the same thing during its early history, roughly 4.5 billion years ago, ejecting countless small bodies into interstellar space as Jupiter and Saturn's growing gravitational influence scattered material throughout the young solar system. If this process is common, and there is strong theoretical reason to believe it is, then the space between stars should be populated by an enormous, largely invisible population of ejected planetary debris, tumbling silently through the emptiness on timescales of hundreds of thousands or millions of years, far outnumbering the planets and stars that get all the attention. Based on these formation models, astronomers before 2017 had already estimated that the density of interstellar objects passing through the vicinity of any given star, including our own Sun, should allow for perhaps one detectable object every decade or so, given the sensitivity of telescopes available at the time. Oumuamua's discovery, arriving within that predicted window, was in one sense a confirmation of decades of theoretical work. The mathematics describing planetary formation and ejection had finally been validated by direct observation. In another sense, though, the object itself defied easy incorporation into those same models, because its elongated shape and unusual acceleration did not closely match what theorists had expected an ejected planetesimal, essentially a leftover chunk of comet or asteroid material, to look like. To place Oumuamua's characteristics in context, It helps to compare it against the general population of objects within our own solar system. The most elongated asteroid previously cataloged in the solar system's main asteroid belt, an object designated 216 Cleopatra, has an aspect ratio of roughly 3:1, itself considered unusually stretched for a solar system body. Oumuamua's estimated ratio of 6:1, and potentially as extreme as 10:1, placed it in an entirely different category, more elongated than anything the asteroid belt or the population of short-period comets had ever produced. Some researchers suggested this extreme shape might itself be a clue to the object's origin, perhaps the product of a violent tidal disruption, an encounter in which a larger parent body passed close enough to its home star to be torn apart by gravitational stresses, stretching fragments into elongated shapes before they were ejected outward into interstellar space. This tidal disruption hypothesis drew on well-documented examples much closer to home. In 1994, fragments of Comet Shoemaker-Levy 9 broke apart after passing close to Jupiter, torn into a string of separate pieces by the gas giant's immense gravitational field, before eventually colliding with the planet's atmosphere in a series of spectacular impacts observed by telescopes worldwide. If a similarly disruptive encounter had occurred in Oumuamua's home system, perhaps as a planetesimal passed too close to its parent star, or a large planet during the system's early chaotic formation period, the resulting fragment could plausibly have emerged with the kind of extreme, elongated proportions observed in 2017. This explanation had the advantage of requiring no exotic new physics, relying entirely on gravitational and tidal processes already well understood from observations within our own solar system. No telescope will ever confirm the precise details of that original event, but the physics involved is understood well enough that a plausible reconstruction, offered here as an illustration rather than a documented fact, can still be built from what is known about how such disruptions unfold elsewhere in the universe. Picture then a young planetary system, somewhere among the stars scattered across the direction of the constellation Lyra, at a time when the sun itself may not yet have existed in anything like its current form. A disk of gas and dust recently collapsed around a newly formed star, still churning with half-built planets and countless smaller fragments, comets, planetesimals, icy rubble left over from the process of formation itself. Among that rubble, a single body, perhaps a kilometer across, orbits quietly for a time, gathering material, growing slowly, the way every planetesimal does during a system's early history. Then, according to the physics that governs every young planetary system, including our own, a larger body passes near it, perhaps a newly formed giant planet, still migrating inward or outward through the disk, its orbit not yet settled into the stable configuration it will eventually hold. The encounter is close enough that gravity itself begins to work unevenly across the smaller body's structure, pulling harder on the side nearest the giant planet than on the side farthest away. Given a body already loosely bound, held together more by weak ice cohesion than by genuine structural strength, that uneven pull is enough. The body stretches, first gently, then dramatically, elongating along the line connecting it to the larger object's center of gravity, exactly as Shoemaker-Levy 9 stretched into its string of fragments before reaching Jupiter in 1994. Unlike Shoemaker-Levy 9, this particular fragment does not go on to collide with anything. Instead, the same gravitational encounter that stretched its shape also alters its orbit, flinging it outward, away from its parent star entirely, at a velocity great enough to escape the system's gravity for good. It carries with it, permanently, the elongated shape imprinted during those final moments of close encounter, a shape with nothing in the emptiness of interstellar space capable of ever reshaping it again. From that point onward, the object simply travels. No collisions to smooth its edges, no atmosphere to erode its surface, aside from the slow, patient bombardment of cosmic rays reddening its exterior year after year, millennium after millennium. No sunlight bright enough at interstellar distances to warm it meaningfully, only the occasional, almost imperceptible tug of a passing star's gravity, nudging its trajectory by fractions of a degree over spans of time too long to meaningfully picture. This reconstruction cannot be verified. It is, by its very nature, unverifiable, offered here as one physically plausible story among several, consistent with everything astronomers have measured, but impossible to confirm without a mission capable of directly sampling material from another star system, a capability that does not yet exist. Extend that same imagined reconstruction forward, across the intervening span of time, and a second scene comes into focus, this one somewhat easier to ground in known physics, because it describes conditions astronomers have studied directly, closer to home. For the first several thousand years after such an ejection, the object would still carry traces of heat left over from its formation, radiating slowly outward into the surrounding cold. Within perhaps 10,000 years, any such residual warmth would have faded entirely, leaving the object's interior at a temperature closely matching the ambient temperature of interstellar space itself, a few degrees above absolute zero, colder than anywhere naturally occurring on Earth, colder even than the coldest recorded temperature on the surface of Pluto. At that temperature, held for hundreds of thousands of years, whatever ices remained within the object's interior would have settled into their most stable possible crystalline structure, locked in place, chemically inert, essentially unchanging for the remainder of the journey. Only the outermost layer, exposed directly to the sparse but relentless bombardment of galactic cosmic rays, high-energy particles accelerated by distant supernova remnants, and other violent astrophysical events scattered across the galaxy, would continue to change it all, slowly darkening and reddening as those particles broke apart and rearranged the simple molecules present near the surface, building up, one collision at a time, across a span of time longer than the existence of most species that have ever lived on Earth. The reddish organic crust spectroscopists would eventually detect in October of 2017. For the vast majority of that journey, nothing eventful happens at all. No collisions, no close encounters. Simply an object tumbling end over end, crossing distances that dwarf anything encountered within a planetary system, at a pace slow enough on a human timescale to make the object's motion appear almost frozen, and fast enough on a galactic timescale to eventually carry it across the entire width of the space separating one star from another. What can be said with confidence is only this: whatever specific sequence of events produced Oumuamua's extreme shape, the physics required to explain it is neither exotic nor unprecedented. It is the same physics already observed reshaping and destroying smaller bodies within our own solar system, simply applied, this time, to a system and a moment in time that no human instrument will ever directly witness. Rotation added a further layer of detail to this picture. Rather than spinning smoothly around a single stable axis, the way most asteroids and comets do, Oumuamua appeared to be tumbling, its rotation more chaotic and irregular, changing its orientation relative to the Sun in a complex pattern rather than a simple repeating cycle. Astronomers modeling the object's light curve found that this tumbling motion was consistent with a body that had experienced some violent event in its past, an impact, a close gravitational encounter, or the same tidal disruption event that may have produced its shape, imparting a chaotic spin that could persist, essentially undamped, for the entire duration of its journey through the near vacuum of interstellar space, where there is nothing to slow such a rotation down. It has likely been tumbling end over end without pause for hundreds of thousands of years. The rotational period itself, the time it took for Oumuamua to complete one full tumble, was calculated at approximately 8 hours, though because the tumbling was irregular rather than simple, different research teams analyzing the same brightness data arrived at slightly different values, ranging from roughly 7 to 8.5 hours, depending on the specific mathematical model used to interpret the light curve. This kind of minor disagreement between research groups, working from the same underlying observations but applying different analytical assumptions, is a normal and expected part of how science handles genuinely novel, unprecedented data. There was, quite simply, no previous example of an interstellar object's light curve to compare against, and every research team was working, in effect, without a template. As the weeks following discovery continued, and as Oumuamua's distance from Earth grew, its brightness dimmed steadily, following the predictable relationship between distance and observed light, familiar from countless other astronomical objects. By early December of 2017, the object had faded to the point where only the largest telescopes on Earth, including the Hubble Space Telescope and the Very Large Telescope in Chile, could still detect it reliably. Each additional week of observation, hard-won and increasingly difficult to obtain, added valuable data points to the trajectory calculations, refining the measurement of that small but persistent non-gravitational acceleration that would soon become the object's most debated characteristic. By the final weeks during which Oumuamua remained observable, astronomers had assembled a portrait of the object built entirely from indirect measurement. No photograph existed that could resolve its actual shape. No spacecraft had come anywhere close to it, and every conclusion rested on the careful interpretation of light, brightness changing over time, color spread across a spectrum, and position tracked against the fixed backdrop of distant stars. This is, in fact, how the vast majority of astronomy is conducted, drawing detailed physical conclusions from patterns of light gathered across enormous distances, and Oumuamua's case represented this method pushed to its absolute limit, a single, fleeting, unrepeatable opportunity to characterize an entirely new class of object using nothing but reflected sunlight gathered by telescopes scattered across the surface of a single small blue planet. That portrait, however complete it seemed at the time, would prove to be only the beginning of the conversation, because once Oumuamua's confirmed characteristics, its extreme shape, its ancient reddish surface, its chaotic tumble, and above all its unexplained acceleration, were published in the scientific literature for the wider research community to examine, the interpretations offered for what those characteristics actually meant would grow far more varied and far more contentious than anyone tracking the object during those first 11 days of observation could have anticipated. The scientific ripple effects of Oumuamua's brief visit extended well beyond the specific debates over its composition and shape. Survey astronomers, aware that the object had been detected almost by chance, using a telescope not specifically designed to hunt for interstellar visitors, began pushing for dedicated instruments capable of catching the next one earlier and observing it for longer. The Vera the 100th Rubin Observatory, then still under construction in Chile, was already expected to dramatically increase the rate at which faint, fast-moving objects could be detected across the entire visible sky, and researchers began recalculating expected detection rates for future interstellar objects based on what Oumuamua's brief appearance had revealed about the sensitivity such surveys would need. This mattered because Oumuamua's greatest limitation, scientifically, was not a lack of interest or effort, but simply timing. It was discovered only after its closest approach to the Sun had already passed, meaning astronomers never observed the object during the period when solar heating and any resulting activity would have been strongest. Every measurement of its acceleration, its color, and its shape came from an object already receding, already cooling, already growing fainter by the day. Had Oumuamua been detected even a few weeks earlier, while still approaching the Sun, the additional data gathered during its closest approach might have resolved several of the outstanding questions about its composition immediately, rather than leaving them open for years of subsequent debate. This limitation shaped how the astronomical community approached the next interstellar visitor when one eventually arrived. It also shaped renewed interest in the idea of an interstellar object rendezvous mission, a spacecraft launched in advance and kept in a kind of standby orbit, ready to alter course and intercept a future interstellar object as soon as one was detected early enough to make a chase feasible. Such a mission had never been attempted, and the engineering challenges involved, matching the extreme velocities of an object like Oumuamua, were formidable, but the scientific payoff of obtaining even a single close-up image or a direct measurement of composition, rather than relying entirely on reflected light gathered from tens of millions of kilometers away, was judged significant enough that serious mission planning began in the years following Oumuamua's discovery. Somewhere, an agency was already asking, what if the next one comes sooner and we are ready this time? None of this engineering effort, however, could change the outcome for Oumuamua itself. By January of 2018, roughly 3 months after its discovery, the object had faded beyond the detection limit of even the most powerful telescopes on Earth, continuing outward on its hyperbolic path at a speed that ensured it would never again come close enough to any star, including our own Sun, to be observed. Its trajectory carries it now toward the outer reaches of the galaxy on a journey that will likely continue, essentially unchanged, for millions or even billions of years, long after every telescope currently operating on Earth has been decommissioned, long after the astronomers who studied it during those 11 frantic days in October of 2017 are gone. What remains in the absence of the object itself is the data, painstaking measurements of brightness, color, position, and velocity gathered by dozens of research teams working independently and cooperatively across the globe, published in journals, debated at conferences, and revisited repeatedly as new hypotheses were proposed and tested against the same fixed set of observations. That data set, small in volume but unprecedented in kind, would go on to fuel one of the more unusual and public scientific controversies of the following several years, a debate that moved this quiet, tumbling fragment of another star system from the pages of specialist journals into a genuinely global conversation. That conversation, and the question it ultimately turned on, whether everything observed could be explained by known natural processes, or whether something more unusual needed to be considered, is where this story continues. In November of 2018, roughly a year after Oumuamua had faded from view, a paper appeared in the Astrophysical Journal Letters that would push the debate over the object's nature far beyond the confines of academic astronomy. Its authors were Shmuel Bialy and Abraham Loeb, both affiliated with the Harvard-Smithsonian Center for Astrophysics, and the paper's central argument was straightforward, even if its implications were extraordinary. The non-gravitational acceleration measured in Oumuamua's trajectory could be explained by radiation pressure, the physical push exerted by sunlight itself, but only if the object were far thinner and lighter, relative to its surface area, than any naturally occurring rock or ice fragment was known to be. The physics behind this argument rested on a simple relationship. Radiation pressure depends on the ratio between an object's surface area and its mass. A dense, solid chunk of rock or ice, even one shaped like an elongated cigar, has too much mass packed into too little surface area for sunlight alone to meaningfully alter its course. But an extremely thin, sail-like structure, something closer to a sheet than a solid body, would have far more surface area exposed to sunlight relative to its mass, and could in principle be pushed by radiation pressure alone, with no need for any outgassing, any escaping ice, any comet-like activity whatsoever. Bialy and Loeb calculated that if Oumuamua's thickness were less than roughly a millimeter, spread across a surface tens of meters wide, radiation pressure alone could produce exactly the acceleration that had been measured. Such a structure, the authors noted, does not occur naturally. No known geological or astrophysical process produces a solid object with those proportions, a sheet thinner than a coin, stretched across an area larger than a football field. The paper's authors proposed, as one possible explanation among several they discussed, that Oumuamua might be an artificial object, potentially a light sail, a form of spacecraft propulsion that uses radiation pressure from a star or from a directed beam of light to accelerate a very thin, reflective structure through space. Light sail technology is not itself speculative. It has been studied seriously by aerospace engineers for decades and tested in small-scale missions launched from Earth, including Japan's Ikaros spacecraft in 2010 and the Planetary Society's light sail missions. What made the Oumuamua proposal extraordinary was not the physics of light sails themselves, but the suggestion that such a structure might have been built by an intelligence beyond our own. A sail, drifting for perhaps 1,000,000 years, catching starlight that was never meant to reach it. The scientific community's response to this proposal was swift and overwhelmingly skeptical. The vast majority of astronomers who studied Oumuamua's data, including many of the same researchers who had tracked the object during its brief visibility in 2017, argued that natural explanations, however imperfect or incomplete, remained far more probable than an artificial origin. Their reasoning followed a principle deeply embedded in scientific practice, sometimes summarized as requiring extraordinary evidence for extraordinary claims. An artificial explanation, however mathematically consistent with the acceleration data, required assuming the existence of an alien civilization capable of building and launching interstellar spacecraft, a claim with no independent supporting evidence, when several natural explanations, incomplete as they were, required no such assumption at all. Researchers including David Jewett of the University of California, Los Angeles, and Alan Fitzsimmons of Queen's University Belfast, both of whom had been closely involved in the original observations, published responses arguing that the same radiation pressure calculation Bialy and Loeb had used could also be satisfied by a natural object with unusually low density, something closer to a loosely bound cluster of ice and dust, sometimes described as a fractal or fluffy aggregate structure, rather than a solid, thin, artificial sheet. Such low-density, porous bodies, while unusual, are not unknown in astronomy. Some comet nuclei and certain types of interplanetary dust particles show similarly low densities, and a sufficiently porous ice-rich body could, in principle, present enough surface area relative to its mass to be measurably affected by radiation pressure without requiring any artificial construction at all. This distinction between an object that is naturally low density and one that is deliberately engineered to be thin became the crux of the ongoing disagreement. Both explanations could mathematically account for the same acceleration data. Neither could be definitively proven or disproven using the observations that existed, because Oumuamua itself was gone, its actual density and internal structure never directly measured, only inferred indirectly from its brightness, its light curve, and its trajectory. This kind of irreducible uncertainty, where multiple competing explanations remain consistent with the same limited data set, is uncommon in modern astronomy, where objects can usually be observed repeatedly, at leisure, until ambiguity is resolved. Oumuamua offered no such luxury. Loeb, for his part, continued to advocate publicly for taking the artificial hypothesis seriously as one possibility among several, rather than dismissing it outright. In 2021, he published a book on the subject titled Extraterrestrial and helped establish the Galileo Project at Harvard University, a research initiative explicitly organized to search for potential technological artifacts, both distant interstellar objects like Oumuamua and closer unidentified aerial phenomena, using a systematic, instrument-based approach rather than speculation or anecdote. The project's stated goal was to apply the same rigorous observational standards used elsewhere in astronomy to a question that had historically been treated as outside the bounds of serious science. This public advocacy drew significant criticism from within the astronomical community, not primarily because researchers objected to the underlying question whether technological artifacts from other civilizations might be detectable, but because many felt the specific case of Oumuamua did not warrant the level of certainty or attention the hypothesis had received in public discourse. Surveys of professional astronomers conducted in the years following the Bialy and Loeb paper found that the overwhelming majority, well over 90% in most polls, considered a natural explanation, however incomplete, substantially more likely than an artificial one. Their position rested not on a rejection of the possibility in principle, but on the standard scientific preference for explanations requiring fewer untested assumptions, particularly when several plausible natural mechanisms, imperfect as each one was, remained on the table. Two explanations, neither provable, neither disprovable, and an object that had already vanished before the argument even began. What this debate ultimately revealed was less about Oumuamua itself, and more about the limits of what a single, brief observation can establish. Every measurement gathered during those 11 days, and the following months of fading visibility, was consistent with more than one physical explanation. This is not in itself unusual in science. Ambiguous data sets requiring further observation to resolve are common. What made Oumuamua's case unusually visible, drawing coverage far beyond typical astronomical findings, was the combination of a genuinely unprecedented object, a physically serious hypothesis proposed by credentialed researchers at a major institution, and a topic, the possibility of extraterrestrial technology, that carries enormous public fascination regardless of its scientific likelihood. The debate did produce one clear, lasting outcome, regardless of which explanation proves correct. It sharpened the astronomical community's understanding of exactly what kind of instruments and observational strategies would be needed to resolve similar ambiguities the next time an interstellar object was detected. Telescopes with greater sensitivity, capable of detecting extremely faint Comet or measuring polarization, a property of light that can distinguish between a solid, reflective sail-like surface and a loosely bound icy aggregate, became a specific, stated priority for observatories preparing to catch the next interstellar visitor earlier and study it more thoroughly than had been possible with Oumuamua. That opportunity, as it turned out, would not take long to arrive. Before that opportunity arrived, however, the scientific community spent several more years testing every remaining natural explanation against the full body of Oumuamua data, refining models that had been proposed in the immediate aftermath of the 2018 acceleration paper. One of the most detailed of these came from Amaya Moro-Martin, a researcher who modeled Oumuamua as a fractal aggregate, a loosely bound structure similar in concept to a dust bunny found under furniture, except composed of ice and rock grains, weakly held together across a volume many times larger than a solid object of the same mass would occupy. Such a structure, Moro-Martin calculated, could plausibly have formed during the early, turbulent history of a planetary system, when small icy grains collide and stick together gently rather than compacting into a dense, solid body. A fractal aggregate of this kind would present enough surface area relative to its mass to experience meaningful acceleration from sunlight alone, without requiring either an artificial origin or the specific, chemically difficult sublimation processes proposed in the hydrogen ice hypothesis discussed earlier. Jane Liu, one of the astronomers credited with the discovery of the Kuiper Belt decades earlier, along with her colleague Eric Fleckau, proposed a related but distinct model in 2019, suggesting that Oumuamua could be understood as a porous, low-density body that gradually eroded as it traveled through interstellar space, losing mass slowly over hundreds of thousands of years due to a combination of cosmic ray bombardment and rare gentle heating events. Their model predicted that such gradual erosion could account for both the object's unusual, elongated shape, produced as weaker portions of the structure flaked away over time, and its non-gravitational acceleration without requiring the fine-tuned assumptions present in either the pure hydrogen ice hypothesis or the artificial light sail hypothesis. Each of these competing models, the fractal aggregate, the hydrogen iceberg, the gradually eroding porous body, and the artificial light sail, shared a common feature that made the entire Oumuamua episode a genuinely unusual case study in how science handles uncertainty. Ordinarily, when multiple explanations compete to account for the same observation, further data collection eventually favors one explanation over the others. Additional observations refine measurements, rule out possibilities, and narrow the field until a single explanation or a small handful of closely related ones remain standing. With Oumuamua, no further observation was possible. The object was gone. Every proposed explanation had to be evaluated using precisely the same, fixed, finite data set gathered during those 11 days in 2017 and the following months of fading visibility, a constraint almost never encountered elsewhere in observational astronomy. An entire scientific debate conducted without the one thing science usually relies on most, the ability to look again. This constraint reshaped how researchers approached the problem. Rather than gathering new data, teams focused on reanalyzing the existing measurements with increasingly sophisticated statistical and physical models, testing each hypothesis not against new observations, but against the internal consistency of the original data, checking whether a given explanation could account for every measured detail simultaneously: the precise shape of the light curve, the exact rate at which the non-gravitational acceleration weakened with distance from the sun, the specific reddish color recorded spectroscopically, and the absence of any detectable coma, all at once, rather than explaining any single detail in isolation while leaving others unaddressed. By most assessments published in the years following the initial debate, no single hypothesis succeeded in explaining every measured detail without at least one significant point of tension. The hydrogen ice model struggled with questions about long-term thermodynamic stability. The fractal aggregate and porous erosion models required assuming a formation and survival history for which there was no direct precedent among any previously observed solar system object. The artificial light sail hypothesis, while mathematically consistent with the acceleration data, required an assumption: the existence of an extraterrestrial technological civilization that carried no independent supporting evidence whatsoever. Astronomy, as a field, generally regards the ability to reproduce every detail of an observation using the fewest necessary assumptions as a mark of a strong explanation. By that standard, Oumuamua's case remained, for years, without a fully satisfying answer. A meaningful shift in this picture arrived in 2023, when researchers Jennifer Bergner and Daryl Seligman published an analysis in the journal Nature, proposing a mechanism that addressed several of the earlier hydrogen ice hypothesis's weaknesses. Rather than requiring Oumuamua to have retained primordial molecular hydrogen ice, frozen since the object's formation and improbably preserved across an interstellar journey lasting hundreds of thousands of years, their model proposed that hydrogen gas could instead be generated more gradually, produced as cosmic rays, and high-energy particles struck ordinary water ice on the object's surface over long periods, breaking water molecules apart and allowing hydrogen to become trapped within the ice structure itself, ready to be released once the object warmed during its pass through the inner solar system. This process, known as radiolysis, the chemical alteration of a material caused by exposure to ionizing radiation, is well documented in laboratory settings and had already been observed affecting ice on other icy solar system bodies, including some of the moons of the outer planets. Applying this known process to Oumuamua's surface offered a way to produce enough hydrogen gas to plausibly account for the measured acceleration using water ice, one of the most common substances found throughout planetary systems, rather than requiring the far more exotic and thermodynamically fragile molecular hydrogen ice proposed in the original 2020 hypothesis. Because water ice is common, chemically stable at a much wider range of temperatures, and consistent with the reddish radiation-processed surface coloring already observed spectroscopically, this radiolysis-based explanation was received by much of the astronomical community as the most physically coherent natural explanation offered to date, though even its authors acknowledged that without direct measurement of Oumuamua's surface, itself now permanently impossible, the hypothesis remained an informed, well-constrained inference rather than a settled conclusion. This is, in many respects, where the scientific understanding of Oumuamua stands today, not with a single universally accepted answer, but with a leading natural explanation, grounded in well-understood chemistry and physics, considered substantially more probable than the alternatives by the overwhelming majority of researchers who have studied the data, while a small number of scientists, most prominently Loeb and his collaborators, continue to argue that an artificial origin cannot be fully excluded and deserves continued serious consideration rather than dismissal. Both positions rest on the same finite, unrepeatable data set gathered in 2017. Neither can be tested further using Oumuamua itself. What changed the broader context of this debate, however, was not any new measurement of Oumuamua, but the arrival of a second interstellar visitor, one that would, for the first time, allow astronomers to ask a different and in some ways more important question. Was Oumuamua typical of what interstellar space sends our way? Or was it, in fact, an unusually strange exception? In August of 2019, less than 2 years after Oumuamua's discovery, an amateur astronomer named Gennady Borisov, observing from a homemade telescope he had built himself in Crimea, detected a faint fuzzy object moving along a trajectory that calculations soon confirmed was hyperbolic, unmistakably interstellar in origin, just as Oumuamua's had been. The object was designated 2I/Borisov, the second confirmed interstellar object, and named following astronomical convention after the individual who first reported it. Unlike Oumuamua, however, this second visitor behaved exactly the way astronomers had long expected an interstellar comet to behave. From the moment of its discovery, 2I/Borisov displayed an obvious, unambiguous coma, a diffuse cloud of gas and dust surrounding its solid nucleus, along with a visible tail stretching away from the sun, the classic signature of cometary activity that had been so conspicuously absent from every observation of Oumuamua 2 years earlier. Spectroscopic analysis of the gas surrounding Borisov detected carbon monoxide at levels significantly higher than typical for comets native to our own solar system, along with cyanogen, water, and other volatile compounds, providing astronomers with direct chemical evidence of the object's composition in a way that had simply never been possible for Oumuamua. Because Borisov displayed clear cometary activity from the moment it was discovered, and because it was detected well before its closest approach to the sun, astronomers had far more time and far better data to study it thoroughly before it too eventually faded from view in 2020. The composition revealed by Borisov's coma turned out to be strikingly familiar. Its ratio of carbon monoxide to water and the overall mix of volatile compounds detected in its tail closely resembled comets that formed in the outer, colder regions of our own solar system, bodies that condensed far from the sun's heat, where ices rich in carbon monoxide remained stable. This similarity suggested that whatever planetary system Borisov originated from, its outer icy regions formed under physical conditions not fundamentally different from those that shaped the distant reaches of our own solar system billions of years ago. In this sense, Borisov's greatest scientific value lay not in raising new mysteries, but in confirming something reassuring. The basic physics and chemistry of comet formation appear to operate similarly across different planetary systems, at least based on this single additional data point. This similarity carried an important implication for how astronomers came to understand Oumuamua's place within the broader population of interstellar objects. If Borisov represented a more typical example, an ordinary interstellar comet behaving exactly as solar system comets do, then Oumuamua's unusual characteristics, its extreme shape, its lack of any detectable coma, its ambiguous acceleration, appeared less like a preview of what interstellar objects generally look like. and more like evidence that the population of objects drifting between stars is genuinely diverse, encompassing both ordinary icy comets like Borisov and rarer, more unusual bodies like Oumuamua, shaped by whatever specific and perhaps violent history each object experienced within its home system before ejection. Statistically, astronomers had always expected some diversity among interstellar objects, since planetary systems throughout the galaxy presumably form under a range of different conditions and eject material through a range of different processes: tidal disruption near a star, gravitational scattering by a giant planet, or catastrophic collision, among others, each of which might produce a differently shaped, differently composed fragment. With a sample size of only 2 confirmed interstellar objects, however, drawing firm statistical conclusions about the overall population remained genuinely difficult. 2 data points can suggest a range of possibilities, but cannot on their own establish which type of object is more common, whether Oumuamua or Borisov better represents the typical interstellar wanderer, or whether both simply represent opposite ends of a wide spectrum of interstellar debris. 2 visitors, 2 stories, and still only the barest beginning of an answer. This is precisely the kind of question that survey astronomers hoped instruments like the Vera the 100th Rubin Observatory, which began its main science operations in the years following Borisov's discovery, would eventually help resolve by dramatically increasing the rate at which faint, fast-moving objects across the entire sky could be detected, rather than relying on chance detections using instruments not specifically designed for the task, as had been the case with both Oumuamua and Borisov. A survey capable of systematically scanning the full sky repeatedly, night after night, promised to increase the expected detection rate of interstellar objects substantially, potentially identifying several per year rather than one every few years, and crucially, identifying them earlier in their approach, while there was still time to direct larger telescopes and potentially spacecraft toward a close, detailed study before the object's brief visibility faded. This anticipated increase in detection capability directly shaped mission planning within the European Space Agency, which had been considering, since shortly after Oumuamua's discovery, a concept for a spacecraft that could be launched in advance and held in a stable holding orbit, ready to be redirected toward a future interstellar object as soon as one was detected with enough advance warning to make a rendezvous possible. Named Comet Interceptor, the mission was formally approved for development, with a design built around exactly the lesson Oumuamua had taught the astronomical community most clearly: that these objects arrive without warning, are visible for only a brief window, and reward whichever instruments are already prepared in advance to make the most of that brief opportunity. Comet Interceptor's design reflects this lesson directly. Rather than being built and launched toward a specific, already known target, in the way most planetary missions are planned years or decades in advance around a predetermined destination, the spacecraft is intended to launch first and wait, parked in a gravitationally stable region of space, until a suitable target, either a pristine, undisturbed comet from the outer solar system or, if fortune allows, a genuine interstellar object, is detected with sufficient advance notice to permit an intercept trajectory to be calculated and executed. This approach represents a significant departure from typical mission planning, born directly out of the specific, frustrating limitation that had shaped both Oumuamua and Borisov's brief visibility: the near-total absence of advance warning before either object's closest approach. Whether Comet Interceptor or a future mission designed along similar lines will ever succeed in reaching a genuine interstellar object during its brief passage through the solar system remains, as of the present, an open question dependent on the timing of both spacecraft readiness and the unpredictable arrival of a suitable target. What is certain is that Oumuamua's discovery permanently changed how the field approaches this category of object, shifting interstellar visitors from a purely theoretical curiosity predicted by statistics but never confirmed into a recognized, if still poorly understood, category of astronomical event that dedicated instruments and mission planning now specifically anticipate. The broader scientific legacy of Oumuamua, then, extends well beyond the specific, unresolved question of what the object actually was. It reshaped survey astronomy's priorities, motivated new spacecraft designs, produced years of theoretical work testing competing physical models against a single fixed data set, and forced the scientific community to publicly confront and largely resolve through argument and evidence, rather than certainty, the question of how seriously to weigh an extraordinary but unprovable hypothesis against several ordinary but imperfect ones. Few objects observed for barely more than 2 weeks have ever produced such a lasting body of scientific work or such a durable public fascination. And yet, for all of that scientific and cultural impact, Oumuamua itself remains, and will likely always remain, an object defined more by absence than by certainty. No photograph exists that resolves its true shape. No spacecraft ever approached closely enough to sample its surface directly. Every conclusion reached about it, its elongation, its color, its chaotic tumble, and its unexplained acceleration, rests on 11 days of reflected sunlight, gathered by telescopes scattered across a single small planet, orbiting a star that, to Oumuamua, was never anything more than a brief gravitational detour on a journey that began long before humanity existed and will continue long after every trace of this observation has been forgotten. It is that quality, an object studied intensely, argued over passionately, and yet never fully known, that carries this story into its final chapters. The slow fading of Oumuamua from view, the silence that followed, and what its brief, unrepeatable visit ultimately left behind. Before that final chapter begins, it is worth returning briefly to Borisov, because its story did not end quietly either. As the comet approached its closest point to the Sun in December of 2019, astronomers tracking it closely began to notice something unexpected. The object appeared to be growing brighter and more active at a faster rate than typical solar system comets usually do at a comparable distance from the Sun, suggesting an unusually volatile rich composition consistent with a nucleus that had spent its entire existence prior to entering our solar system in the extreme cold of interstellar space, far colder than even the outer reaches of our own solar system ever reach, preserving more of its original volatile ices intact than a typical long-period comet, which has usually made at least one previous close pass by the Sun, would retain. Then, in March of 2020, roughly 3 months after its closest solar approach, observers noted a sudden, unmistakable brightening and structural change in Borisov's nucleus, a signature strongly suggesting that the comet's solid core had partially fragmented, breaking apart under the combined stress of solar heating and the object's own rotation. Fragmentation events like this are not unheard of among solar system comets. Sun-grazing comets in particular are sometimes observed breaking apart entirely as they pass extremely close to the Sun, but observing this kind of structural failure in a confirmed interstellar object provided rare direct evidence about the physical strength, or in this case relative fragility, of material formed in another star system. The fragmentation suggested that Borisov's nucleus, whatever its precise internal structure, was not a single solid cohesive body, but something more loosely bound, weaker under stress than many solar system comet nuclei, a detail that added yet another data point to the broader question of how interstellar objects are typically constructed. By comparing Borisov's apparent fragility with Oumuamua's extreme elongation and chaotic tumble, some researchers proposed that both objects, despite their very different observed behaviors, might share a common underlying characteristic: relatively weak internal cohesion, structures held together loosely enough to be reshaped, elongated, or even partially fragmented by the stresses of tidal encounters, rotational spin-up, or solar heating. If this proves true for a larger sample of future interstellar objects, it would suggest that material ejected from forming planetary systems tends on average to be structurally weaker and more loosely bound than the more solid compacted bodies typically found closer to the centers of mature solar systems, a conclusion with implications for models of how planetary systems form and shed material during their earliest, most chaotic years. Two objects torn from different stars, both showing, in their own way, how fragile the leftovers of planet formation can be. The statistical challenge of drawing broad conclusions from only two confirmed examples remained throughout this period, a persistent limitation on how confidently astronomers could generalize. Based on the detection rates achieved by pan-stars and other existing survey telescopes operating during the years surrounding Oumuamua and Borisov's discoveries, researchers estimated that the overall density of interstellar objects passing through the vicinity of the Sun, most of them far too small or faint to ever be detected by current instruments, could be on the order of several times 10 to the 15th objects for every cubic parsec of space, an almost incomprehensibly large number that, when translated into practical terms, still implies that only a small handful of objects large enough and bright enough to detect should pass close enough to Earth to be noticed within any given decade, using instruments available before the completion of next-generation survey telescopes. This is precisely the gap the Vera, the 100th, Rubin Observatory, officially beginning its main 10-year survey operation in the years following Borisov's fragmentation, was specifically designed to close, equipped with the largest digital camera ever built for astronomical use, and programmed to photograph the entire visible southern sky repeatedly, roughly every few nights. The observatory's legacy survey of space and time was projected based on pre-launch simulations published by the survey's planning team to increase the expected detection rate of interstellar objects substantially, with some models suggesting the survey could identify multiple new interstellar objects over the course of its planned operational lifetime, a dramatic increase compared to the roughly one confirmed detection per 2 years achieved by earlier generation instruments. Achieving that detection rate would transform the study of interstellar objects from a field built around isolated, unrepeatable encounters into something closer to a genuine statistical science, one in which patterns across dozens of objects, rather than conclusions drawn from a single unusual example, could finally be tested. A larger sample size would allow astronomers to determine, with actual statistical confidence, whether objects resembling Oumuamua's extreme, elongated shape and ambiguous acceleration represent a common outcome of planetary system formation and ejection, or whether Oumuamua instead represented a genuine outlier, a rare, unusual specimen, unlike the majority of what interstellar space typically sends toward the inner solar system. This uncertainty, whether Oumuamua was typical or exceptional, sits at the heart of why the object continued to generate scientific interest and public fascination for years after it had become permanently undetectable. In most areas of astronomy, a single unusual observation eventually gets placed in context, understood as either representative of a broader class of objects or as a genuine rarity once enough additional examples have been gathered for comparison. Oumuamua's case remained suspended in that uncertainty for an unusually long time, a single brief data point whose true significance, ordinary or exceptional, could not be resolved using the tools available during the years immediately following its discovery. Public interest in the debate, meanwhile, showed little sign of fading, driven in large part by the accessibility of the central question at its core. Unlike many scientific controversies, which turn on technical details difficult for a general audience to evaluate, the Oumuamua debate could be summarized in a single intuitive question that required no specialized training to grasp. Was this strange object natural, or was it not? That question, stripped of its underlying statistical and physical complexity, proved durable enough to sustain coverage across documentaries, popular science books, and ongoing public discussion for years, even as the underlying scientific debate, conducted through peer-reviewed papers and conference presentations, gradually settled toward a strong, though not universal, consensus favoring a natural explanation. That gap between a scientific community converging gradually and unevenly toward a probable natural answer and a public conversation that often preferred the more dramatic possibility left open by that very uncertainty became its own subject of interest among researchers who study how scientific findings are communicated and understood outside of academic settings. Oumuamua, in this sense, became not only an astronomical case study, but something closer to a case study in the sociology of scientific uncertainty itself, an object whose genuine, unresolved ambiguity offered something for nearly every kind of curiosity to hold on to. One additional case, closely tied to this same debate, deserves mention here, if only because it illustrates how quickly claims of a third interstellar visitor can generate controversy of their own. In 2019, Loeb and a graduate student, Amir Siraj, published an analysis of a small meteor, a fragment of interplanetary or possibly interstellar material that had burned up in Earth's atmosphere in January of 2014, years before Oumuamua's discovery, after being recorded by government sensors designed to monitor atmospheric fireballs. Based on the recorded velocity data, Loeb and Siraj argued that this small object, cataloged as Cineos January 8, 2014, had likely originated from outside the solar system, potentially making it the first interstellar object ever detected, predating Oumuamua by more than 3 years, simply unrecognized as such at the time because no one had been specifically looking for interstellar trajectories among atmospheric fireball data. This claim proved considerably more difficult to verify than either Oumuamua's or Borisov's confirmed interstellar status, largely because the velocity measurements underlying it came from sensors designed for national security purposes, whose precise calibration data remained classified and unavailable for independent scientific review. Several astronomers, including researchers who had closely studied both confirmed interstellar objects, expressed considerable skepticism about the claim, noting that without access to the original uncalibrated instrument data, the reported velocity, and therefore the conclusion that the object's trajectory was genuinely hyperbolic rather than simply the result of measurement uncertainty, could not be independently confirmed to the standard normally required for such an extraordinary claim. In 2022, United States Space Command issued a memo stating that the government's own analysis supported the interstellar origin of the 2014 meteor with a stated level of confidence, a development Loeb and Siraj cited as vindication. This did not fully resolve the scientific disagreement, however, since the underlying calibration data that would allow independent astronomers to verify the claim through standard peer-reviewed methods remained unavailable to the broader research community, leaving the object's status as a confirmed interstellar visitor considerably more contested within the astronomical literature than either Oumuamua's or Borisov's well-documented, independently verified hyperbolic trajectories. A third visitor, perhaps, burned to nothing in an ordinary January sky years before anyone thought to look for it. This episode, contested and unresolved as it remains, underscores a broader pattern that runs through the entire story of interstellar object research. Confirmation in this field depends entirely on the availability of precise, verifiable measurement, and the moment that verification becomes difficult or impossible, whether because an object has permanently faded from telescopic range, as with Oumuamua, or because the underlying data remains restricted, as with the 2014 meteor, scientific consensus becomes correspondingly difficult to reach, regardless of how compelling any individual interpretation of the available evidence might seem. What ties Oumuamua, Borisov, and this contested 2014 meteor together, beyond their shared classification as objects of interstellar origin, is the way each case illustrates a fundamental asymmetry at the heart of this entire field of study. These objects arrive without warning, remain observable for only a brief window, measured in weeks or, in the meteor's case, mere seconds, and then vanish permanently, either receding beyond detection range or, in the most extreme case, disintegrating entirely in Earth's own atmosphere. Every conclusion astronomers draw about them must be extracted from whatever data happen to be gathered during that narrow, unrepeatable window, using whatever instruments happen to be pointed in the right direction at the right time. It is a form of science conducted almost entirely in retrospect, piecing together the physical nature of a visitor from another star system, using only the fragments of light, velocity, and trajectory data that chance and human preparedness allowed to be captured before the opportunity closed forever. Oumuamua remains, among all of these cases, the one that captured the public imagination most completely, not because its evidence was the strongest, but perhaps because its evidence was the most incomplete, leaving just enough genuine, unresolved scientific uncertainty for both careful natural explanations and far more provocative possibilities to remain, for now equally impossible to fully rule out. Taken together, the body of research produced in the years following Oumuamua's discovery, the competing physical models, the public debate over its origin, the arrival and study of Borisov, the contested case of the 2014 meteor, and the resulting shift in how observatories and space agencies now prepare for the next interstellar visitor, represents an unusually complete example of how science handles a genuinely singular event. There was no laboratory experiment to repeat, no second sample to gather, no way to simply wait and observe again under better conditions. Every conclusion had to be built, carefully and often contentiously, from a fixed, finite record, and even now, years later, that record continues to be reanalyzed and reinterpreted as new theoretical tools and new comparison objects become available. There is something worth sitting with in that fact alone. An object roughly the length of a football field, tumbling silently through the dark for perhaps 1,000,000 years or more, crossed paths with a small blue planet for 11 brief days, allowed itself to be measured and argued over, and then continued on, indifferent, toward a destination no telescope will ever confirm. Whatever Oumuamua truly was, an ordinary fragment of ice and rock shaped by violence long ago, or something else entirely, it has already passed beyond the reach of every question still being asked about it. That departure, the slow fading of a single point of light from the world's most powerful telescopes, and everything the astronomical community has done since, in the years that followed, in response to it, is where this story now turns. That anticipated shift, in fact, is no longer only a matter of future planning. The Vera the 100th Rubin Observatory, perched on a mountain summit in the Chilean Andes and equipped with the largest digital camera ever built for astronomical use, formally began its 10-year legacy survey of space and time in the summer of 2026 after a lengthy period of engineering validation and calibration, scanning the entire visible southern sky roughly every few nights using a camera capable of capturing more than 3,000 megapixels in a single exposure. The observatory is now generating millions of individual alerts each night, flagging objects whose brightness or position has changed since the previous observation, precisely the kind of signal that would reveal a new interstellar object moving rapidly against the fixed background of stars. Within its first weeks of operation, the survey had already identified thousands of previously uncatalogued asteroids within our own solar system, an early demonstration of the detection power astronomers have spent years anticipating, and the same power that may, in the coming years, finally deliver the larger, statistically meaningful sample of interstellar visitors that Oumuamua and Borisov on their own could never provide. Every additional interstellar object this new survey identifies will be compared almost automatically against the two that came before it, tested against Oumuamua's extreme elongation and ambiguous acceleration, and against Borisov's more familiar, comet-like activity, gradually building the kind of statistical foundation that a sample size of 2 could never support. For now, though, Oumuamua remains what it has been since October of 2017, the first, the strangest, and still the most argued over example of a visitor from beyond our sun, a brief flash of reflected light that arrived without warning, resisted easy explanation, and disappeared long before the questions it raised could be fully answered. That anticipation, as it turned out, did not need to wait for Rubin Observatory's cameras to begin their systematic decade-long survey. On July 1st, 2025, more than a year before the legacy survey of space and time formally began, the Atlas Survey Telescope, a NASA-funded network designed primarily to watch for asteroids on a possible collision course with Earth, detected a faint, fast-moving object from its station in Rio Hurtado, Chile. Within hours, astronomers combing through archived images from other survey telescopes found earlier, unrecognized detections of the same object stretching back to mid-May, pre-covery data that allowed the object's orbit to be calculated with unusual speed and confidence. The trajectory was unmistakably hyperbolic, with an eccentricity of roughly 6.1, several times more extreme than Oumuamua's already unprecedented value, and a velocity relative to the Sun of approximately 58 kilometers per second. A third interstellar object had arrived, and this time, astronomers caught it early. The object received the designation 3I/Atlas, following the same naming convention established for Oumuamua and Borisov, the number marking its place as the third confirmed visitor from beyond the solar system, and the name crediting the survey that found it. Unlike Oumuamua, and very much like Borisov before it, 3I/Atlas showed unambiguous cometary activity from nearly the moment it was found. Deep imaging revealed a coma, a surrounding envelope of gas and dust, and spectroscopic analysis quickly identified its composition as unusually rich in carbon dioxide, with only faint traces of water vapor detectable even as the object approached within a few astronomical units of the Sun. This particular chemical signature, strong carbon dioxide activity paired with weak water emission at a distance where water ice would ordinarily already be sublimating rapidly, suggested a nucleus containing large reservoirs of highly volatile ices, material that may never have been significantly warmed since the object's formation, offering a rare, relatively unaltered sample of the icy building blocks present in another planetary system. A third messenger, and this time the ice itself began speaking before anyone had to ask. The scale of observational effort directed at 3I/Atlas during the following months exceeded anything mounted for either of its two predecessors. The Hubble Space Telescope captured detailed images showing a distinct teardrop-shaped cocoon of dust surrounding the nucleus. The James Webb Space Telescope in December of 2025 detected methane within the coma, an extremely volatile compound that sublimates at temperatures even lower than carbon dioxide, adding further evidence that this object's ices had spent most of their existence in an extremely cold environment, consistent with an origin far from any star's warmth for an extended period. Because the comet's path carried it relatively close to Mars during its approach toward the Sun in October of 2025, the European Space Agency redirected 3 separate spacecraft already stationed in the vicinity: Mars Express, the ExoMars Trace Gas Orbiter, and the Jupiter Icy Moons Explorer, to observe the object from vantage points no Earth-based telescope could match, gathering data that continues to be analyzed. Size estimates for 3I/Atlas's solid nucleus evolved considerably as more data arrived, a pattern familiar from Oumuamua's own observation history, though for different reasons. Early measurements, complicated by the difficulty of separating the faint glow of the solid nucleus from the much brighter surrounding coma, placed the upper limit on its diameter as high as 5.5 kilometers. Later analysis, conducted after the comet's closest approach to the Sun in late October of 2025, once the geometry of observation improved, refined this estimate to approximately 2.5 kilometers, still substantially larger than either Oumuamua's estimated few hundred meters or Borisov's roughly similar small scale, making 3I/Atlas, by a wide margin, the largest confirmed interstellar object yet observed. That size, combined with the survival of a substantial fraction of its original mass through its closest approach to the Sun, meant that 3I/Atlas, unlike some smaller comets that disintegrate entirely under the stress of solar heating, remained largely intact throughout its passage, continuing to outgas steadily as astronomers tracked its position with a precision and duration Oumuamua's brief, faint visibility had never permitted. In March of 2026, the comet passed within roughly 54 million kilometers of Jupiter, a distance close enough to noticeably perturb its outbound trajectory through the giant planet's gravitational influence before continuing its journey back out toward interstellar space, never to return. 54 million kilometers from Jupiter, close enough to feel its pull, far enough to survive it. As with Oumuamua 8 years earlier, 3I/Atlas's unusual characteristics, its size, its carbon dioxide-rich chemistry, and certain irregularities noted in its jet structure and light curve, prompted renewed public speculation about an artificial origin, with Loeb once again publishing analyses cataloging what he described as a lengthy list of physical anomalies, warranting further scrutiny before a purely natural explanation could be considered fully settled. This time, however, the sheer volume and quality of data available, direct spectroscopic confirmation of active outgassing, X-ray observations by Japan's EXORISM satellite detecting the interaction between escaping cometary gas and the solar wind across a debris cloud stretching some 400,000 kilometers, and steadily refined mass estimates that fell far short of what a deliberately engineered structure would require, allowed the broader scientific community to reach a confident consensus considerably faster than had been possible with Oumuamua. The evidence, gathered across dozens of instruments and multiple space agencies working in coordination, pointed clearly and consistently toward an unusually large, chemically distinctive, but entirely natural comet. What makes this pattern worth pausing on is not simply that the artificial hypothesis was raised again and set aside again, but what the repetition itself reveals about how this particular scientific debate now operates. Each time an interstellar object arrives, carrying some unexplained detail, whichever specific anomaly happens to resist easy explanation in the moment, a portion of the conversation reaches immediately for the most extraordinary possible interpretation, while the broader research community works, often for months or years, to test whether a natural mechanism, however unusual, can account for the same observation without requiring any assumption beyond known physics and chemistry. With 3I/Atlas, that process moved faster and reached a firmer resolution than it had with Oumuamua, not because the object was inherently less strange, but because it arrived earlier in its approach, remained observable far longer, and was met by an observational infrastructure, including instruments and international coordination, that simply did not exist in 2017, built up substantially in direct response to the questions Oumuamua itself had first raised. A separate line of research, running alongside the debates over composition and origin already described, attempted to answer a different question entirely, not what Oumuamua was made of, but which star it might have come from in the first place. In 2018, a team led by Corian Baylor-Jones of the Max Planck Institute for Astronomy used data from the European Space Agency's Gaia satellite, which had recently mapped the precise positions and motions of more than 1 billion stars across the galaxy, to trace Oumuamua's trajectory backward through time, searching for any star whose own path might have crossed close enough at low enough relative speed to plausibly have been its point of origin. The search identified 4 candidate stars whose past positions came within roughly 2 light-years of Oumuamua's reconstructed path, at speeds low enough to be broadly consistent with an ejection event. The closest of these, a small reddish dwarf star catalogued as HIP 3757, appeared to have passed within about 2 light-years of Oumuamua's trajectory roughly 1 million years ago. None of the 4 candidates, however, showed any confirmed evidence of hosting a giant planet, the kind of massive body whose gravity would ordinarily be required to fling a smaller object outward at the velocities Oumuamua displayed, and none of the 4 could be confirmed, with the data available at the time, as Oumuamua's true point of origin. The authors of the study were careful to note that their search covered only a small fraction of the galaxy's total stellar population, making it, by their own estimate, unlikely to have actually captured the correct home system by chance. That search remains open. Later releases of Gaia data, covering a larger and more precisely measured sample of stars, may eventually narrow the possibilities further, though even then, definitively identifying a single origin star among the hundreds of billions scattered across the galaxy may simply remain beyond what the available data can support. Oumuamua's true point of departure, in other words, may never be known with certainty, only narrowed gradually to an ever smaller list of plausible candidates. One particular episode within the 3I/Atlas story illustrates especially clearly how self-correcting this entire process tends to be. In the weeks following discovery, before the comet's true nature had been fully characterized, preliminary estimates of its mass, calculated from early, incomplete brightness and size data, suggested a value in the tens of billions of tons, a figure that some public commentary seized upon as further evidence of something unusual, even artificial, about the object. As more precise measurements arrived, particularly detailed imaging from the Hubble Space Telescope that finally separated the solid nucleus from the surrounding coma, and later X-ray observations from Japan's X-RISM satellite that directly measured the scale and behavior of gas escaping from the nucleus. That mass estimate was revised downward by a factor of roughly 700, settling closer to 44 million tons, a figure fully consistent with an ordinary, if unusually large, cometary nucleus composed of ice and rock. This kind of dramatic revision, an early estimate later corrected by several orders of magnitude, is not a sign of scientific failure. It is closer to the opposite, a demonstration of exactly how the field is supposed to work when it encounters something unprecedented, gathering better data, applying better instruments, and revising conclusions accordingly, however different the final number turns out to be from the first. The XRISM measurements in particular provided something genuinely new to this entire line of research, a direct look at the physical scale of gas being shed by an interstellar object, stretching outward across roughly 400,000 kilometers, produced through the same basic physics that drives outgassing in any solar system comet, just observed for the first time in a body that had never been part of our solar system at all. Taken together, the three confirmed interstellar objects observed as of today tell a story of genuine diversity rather than a single, repeating pattern. Oumuamua arrived small, dry in appearance, extremely elongated, tumbling chaotically, and accelerating in a way that has still never been fully, unambiguously explained. Borisov arrived as an ordinary, if unusually carbon monoxide-rich comet, behaving almost exactly as pre-2017 theoretical models predicted an interstellar visitor should. And 3I/Atlas arrived larger than either of its predecessors, its coma dominated by carbon dioxide and methane rather than water, hinting at formation and storage conditions perhaps colder, or perhaps simply different, from anything represented in our own solar system's icy reservoirs. Three objects, three distinct compositions, three different physical stories, drawn from what must be an immense and varied population of debris scattered across the galaxy by the routine, violent process of planetary system formation happening around countless other stars. It is against this backdrop, three confirmed visitors now studied, one of them still defying full explanation nearly a decade after it first appeared and vanished again within a matter of weeks, that Oumuamua's own particular story approaches its quiet ending. With 3 confirmed examples now available for comparison, researchers have begun cautiously refining the statistical models first developed decades before Oumuamua's discovery. The rate of detection, roughly 1 confirmed interstellar object every few years, using instruments not originally optimized for the task, combined with the compositional diversity observed across all 3 visitors, suggests a galactic population shaped by many different formation and ejection histories rather than a single, uniform type of debris. Some fraction of this population likely consists of ordinary volatile-rich comets, similar to Borisov and 3I/Atlas, material ejected relatively gently from the outer icy regions of forming planetary systems. A smaller fraction may resemble Oumuamua, fragments shaped by more violent processes, close stellar tidal encounters, catastrophic collisions, or long-term erosion during transit that leave a more unusual physical signature behind. This diversity carries an implication that runs in both directions. Just as our solar system has, over billions of years, received a small but steady trickle of material ejected from other planetary systems, our own solar system has almost certainly done the same in reverse, flinging its own comets, asteroids, and icy planetesimals outward into interstellar space during the chaotic early period of planet formation, and periodically since, whenever a comet's orbit brings it close enough to Jupiter or another giant planet to be gravitationally ejected entirely. Some fragment of the material that once orbited our own sun, perhaps even material similar in composition to the comets studied by missions like Rosetta or Stardust, is very likely drifting through interstellar space at this moment, indistinguishable to any observer light years away from the objects our own telescopes have spent the last decade struggling to characterize. This symmetry connects to a long-standing, still unresolved hypothesis in astrobiology known as lithopanspermia, the idea that microbial life, if it exists anywhere within a planetary system, might occasionally be transported between stars, embedded within ejected rock or ice fragments, shielded from the harshest radiation of interstellar space by a sufficient thickness of surrounding material. The hypothesis, first proposed in a modern scientific form by researchers including Fred Hoyle, and later developed further by scientists such as Paul Wesson, remains almost entirely theoretical, constrained heavily by the extreme difficulty any biological material would face surviving the timescales involved, potentially hundreds of thousands of years of transit, combined with intense exposure to galactic cosmic rays capable of breaking down organic molecules over exactly those kinds of durations. Oumuamua's own reddish radiation-processed surface, discussed earlier in this story, offers an indirect but relevant data point in this ongoing scientific conversation. If a surface exposed for an estimated hundreds of thousands of years to cosmic radiation accumulates the kind of organic crust spectroscopists identified, then any biological material embedded near that same surface would very likely face destruction across a similar timescale, while material buried more deeply within a sufficiently large object, protected by several meters of overlying rock or ice, might in principle survive considerably longer. This distinction between a fragile, radiation-scoured exterior and a potentially better shielded interior is precisely the kind of detail that direct sample collection from an interstellar object, something no mission has yet accomplished, would be needed to meaningfully resolve. Some fragment of our own solar system may already be drifting toward another star, carrying perhaps nothing more than rock and ice, Perhaps in some far more speculative scenario, something more. For now, this remains firmly in the realm of grounded but unconfirmed hypothesis, discussed seriously within astrobiology research programs, including studies conducted in connection with NASA's Astrobiology Institute, but resting on no direct observational evidence from any of the 3 interstellar objects examined so far. None of Oumuamua, Borisov, or 3I/Atlas showed any spectroscopic signature suggesting the presence of biological material, and the overwhelming majority of researchers studying lithopanspermia treat it as a mathematically interesting possibility worth continued study, rather than a claim supported by current evidence. It remains one of the many open questions that the study of interstellar objects, still in its earliest years as an observational science, has not yet been equipped to answer. What can be stated with confidence, based on everything gathered across 8 years and 3 separate visitors, is this: our solar system is not an isolated system sealed off from the rest of the galaxy. It is, and has always been, connected to countless other planetary systems by a slow, continuous exchange of material, drifting across unimaginable distances and unimaginable stretches of time, occasionally, rarely, briefly passing close enough for a telescope on a small blue planet to notice, measure, argue over, and then watch disappear again into the dark. Oumuamua itself continues that journey right now, exactly as it has every moment since the sun's gravity released it back into the emptiness beyond the planets. Its outbound velocity, once it had cleared the sun's gravitational influence, settled to approximately 26 kilometers per second relative to the solar system's own motion through the galaxy, considerably slower than the 87 kilometers per second recorded during its closest approach, a difference explained entirely by the sun's gravity pulling the object inward on the way in, and then releasing that same energy back as the object climbed back out by the early 2020s. Oumuamua had already crossed the orbit of Neptune, leaving behind the last of the solar system's major planets, and its path now carries it in the general direction of the constellation Pegasus, though the star field it will eventually pass through, if it passes near any star at all, remains far too distant and far too uncertain to predict with any real confidence. At its current speed, Oumuamua will cover a single light-year of distance in roughly 11,000 years, a figure that on its own offers one of the clearest possible illustrations of the sheer scale of interstellar space. 11,000 years is longer than the entire span of recorded human history, longer than agriculture, longer than any city, any written language, any civilization that has ever existed on Earth, and it represents the time required for this single object to cross a distance so small on a galactic scale that astronomers use it as their basic unit of measurement almost apologetically, aware that even a light year barely begins to describe the true emptiness Oumuamua is now moving through. 11,000 years to travel a single light year, and it has millions of years left to travel. There is no telescope currently operating, and likely none that will ever be built using any foreseeable technology capable of detecting Oumuamua again. Its light has faded permanently below the threshold of observation, and its position, while still calculable using the orbital mechanics established during those 11 days of study in 2017, exists now only as a mathematical projection, a line drawn forward from the last confirmed measurements, extending into a future no instrument will ever confirm. The object itself, whatever its true composition, whatever specific violence or gentle process shaped its extreme elongated form, continues its slow, silent tumble, indifferent to the arguments still being published about it, indifferent to the missions being designed in hopes of reaching whatever comes after it, indifferent to the fact that, for 11 brief days in the autumn of 2017, an entire species on a small, warm planet stopped to watch it pass. Somewhere on Earth, meanwhile, mission planners continue refining the design of spacecraft meant to do what no instrument managed with Oumuamua, Borisov, or even 3I/Atlas, reach one of these visitors directly while it is still close enough to intercept. The European Space Agency's Comet interceptor remains parked in its planning stages, waiting for a launch window, and after that, waiting again patiently for a target worth chasing. Whether it succeeds, whether any mission ever succeeds, remains unknown. What is known is that each new interstellar object, each brief, unrepeatable visit, adds one more data point, one more piece of a picture that is still, after 3 examples, barely beginning to take shape. That picture will keep filling in, slowly, over years and decades, long after tonight. But for now, the story of Oumuamua itself has reached its quiet end. For most of recorded human history, an object like this would have meant something entirely different to whoever happened to look up and notice it. Comets, for most of that history, were read as omens, warnings, disruptions in an otherwise fixed and orderly sky. It took centuries of careful observation and the work of astronomers like Edmund Halley, who first calculated that a comet's return could be predicted using the same laws of motion governing the planets, to reveal that these visitors were not messages meant for us at all, but simply matter following the same physics as everything else in the sky, indifferent to human affairs entirely. Oumuamua arrived into a world already shaped by that centuries-long shift, a world equipped for the first time in human history with instruments precise enough to measure a faint, fast-moving object's brightness night after night, calculate its orbit within hours, and coordinate a global response within days. It arrived, in other words, at almost exactly the moment human civilization had finally built the tools capable of truly seeing it for what it was. That timing, more than anything else in this story, is worth resting on for a while now. 11 days, that is all it took. It arrived without warning in October of 2017. It is impossible to say precisely why it took that path. Astronomers watched it for 11 days. They argued about it for 8 years. They still are, in a sense. Somewhere out past Neptune's orbit, past the edge of everything familiar, it is still moving. 26 kilometers every second, silent, tumbling. In, carrying a reddish crust, built one cosmic ray at a time over hundreds of thousands of years. Out, carrying a shape no other object in our solar system has ever matched. A little more than 400 meters long by the best available estimate, and perhaps only 40 meters wide. 10 times as long as it is wide, no solar system asteroid has ever come close to that proportion. Moving through a darkness so complete that the nearest star, other than our own, is still 4 light-years away. It will not reach that star. It will not reach any star, not for a very, very long time. Millions of years, most likely, perhaps longer. There is nothing rushing it now. There is nothing slowing it down. Only the occasional, almost imperceptible pull of a distant star's gravity, bending its path by fractions of a degree, over spans of time too long to meaningfully imagine. It carries no engine, no fuel, no name written anywhere on its surface. Only the momentum it was given once, long ago, when whatever violence shaped it first sent it outward. A tidal encounter, perhaps, a collision, a close pass by some star's own gravity, gone slightly wrong, gone slightly too close. No one will ever know exactly which. What is known is this: somewhere in another planetary system, one that formed the same way ours did, out of a slowly collapsing cloud of gas and dust, something broke loose. It has been falling, essentially, ever since, falling through emptiness rather than falling toward anything in particular. For most of that fall, no telescope existed anywhere to notice it. For 11 days, one did. That is the whole of the encounter. 11 days out of what may be 1,000,000 years of travel. A fraction so small it is difficult to even express meaningfully, less than 100,000th of the whole. And yet within that fraction, an entire body of scientific literature was written. Hypotheses proposed, hypotheses discarded. New instruments designed in direct response to be ready the next time. 2 more visitors have already followed. 2I/Borisov, an ordinary comet behaving exactly as the textbooks predicted. Then 3I/Atlas, larger, stranger in its own way, its coma rich with carbon dioxide and methane, its nucleus surviving a close pass by the sun that many smaller comets would not have survived. 3 visitors, 3 different stories, one shared origin, somewhere among the countless other stars scattered across this single, ordinary galaxy. It does not know it was ever seen. It does not know it was ever argued about. It simply continues. The way it has continued since before agriculture, since before writing, since before the pyramids, before Rome, before anything resembling the modern shape of human civilization. The way it will continue long after all of that is gone too. Long after the telescopes that once watched it have been decommissioned. Long after the papers written about it have been forgotten, filed away in archives no one thinks to open. It will still be out there, still red, still cold, still tumbling end over end through a silence far older than any of us. Consider for a moment just how far Oumuamua still has to go before it leaves the sun's influence entirely. The solar system does not simply end at Neptune's orbit, the last major planet, roughly 4.5 billion kilometers from the sun. Beyond Neptune lies the Kuiper Belt, a vast disc-shaped region of icy bodies, including Pluto, that Oumuamua crossed through years ago, largely unaffected by anything within it, moving too quickly and too far from any individual object to be meaningfully influenced by its gravity. Beyond the Kuiper Belt lies something far larger still, the Oort cloud, a vast spherical shell of icy debris theorized to surround the entire solar system, stretching out to a distance of perhaps 100,000 astronomical units, roughly a light year and a half from the sun. This is the true edge of the sun's gravitational influence, the boundary where its pull finally becomes too weak to hold anything in orbit any longer. Oumuamua will spend tens of thousands of years crossing that outer region alone, moving through a volume of space that dwarfs everything discussed so far in this story before it can be said to have truly left the solar system behind. Only then does interstellar space, in the fullest sense, begin again. The same interstellar space it emerged from, sometime in the distant past, in the same interstellar space it is now returning to, carrying with it every measurement, every argument, every unresolved question raised about it here tonight. None of that argument matters to the object itself, of course. It has no awareness of any of it. What it has, instead, is momentum, a steady, unhurried drift, established long before human beings existed to notice it, and destined to continue long after every trace of that noticing has faded. There is something quietly settling in that thought, an object that predates human civilization, that will very likely outlast human civilization, briefly shared 11 days with us, and asked nothing in return. It did not pause. It did not slow down to be studied. It simply happened to pass close enough for a handful of days, for a handful of telescopes scattered across a single small planet to catch its reflected light. Dozens of observatories spread across 4 continents, coordinated across time zones and language and institutional boundaries, in order to gather as much data as possible before that narrow window closed. That kind of cooperation, quiet and largely unnoticed outside the scientific community itself, is a small, grounded thing worth pausing on for a moment. A shared global effort, mounted quickly and without argument, in response to a single faint point of light moving strangely against a fixed background of stars. It asked nothing of the people who studied it. It offered no explanation, no confirmation, no resolution to any of the questions its own behavior raised. It only allowed itself to be watched for 11 days before continuing on. That is enough. That was always going to have to be enough. Whatever Oumuamua truly is, wherever it truly came from, whatever violent or gentle history shaped its strange, elongated form, it has already told us everything it is ever going to tell us. The rest, the debate, the competing models, the unresolved questions, belongs now to us alone, not to the object. It has already moved on. This is, in the end, what the study of Oumuamua leaves behind. Not a final answer, not a resolved mystery. Consider the speed involved, one more time, from a different angle. 26 kilometers per second is faster than Earth itself moves around the Sun, which travels at just under 30 kilometers per second along its own orbital path. Oumuamua is not orbiting anything. It is simply passing through, at a pace comparable to our own planet's motion, except heading outward, forever, rather than curving back around. At that speed, it could cross the entire distance between the Earth and the Moon in under 4 hours. It could cross the continental United States in under 2 minutes. Numbers like these are useful and also, in their own way, almost meaningless. The human mind is built to understand distances measured in footsteps, in city blocks, in the length of a familiar drive. It is not built to intuitively grasp a light year, let alone the tens of thousands of light years that separate our sun from the far side of our own galaxy. What the mind can do, instead, is hold a single, smaller fact steady and let that fact stand in for the larger one it cannot quite picture. 11 days. That is the fact this story keeps returning to. That is roughly how long it takes the Moon to complete about a third of its own orbit around the Earth. It is shorter than most people's paid vacation time in a given year. And it is the entire span of direct observational knowledge that exists, and will ever exist, about an object that may have been traveling for longer than the human species itself. That is not a failure of effort. Astronomers on 4 continents worked as quickly and as carefully as the situation allowed, publishing findings within days rather than the months or years such analysis normally takes. It is, instead, simply the nature of this particular kind of science. A science built almost entirely around brief, unrepeatable windows, chance alignments between a fast-moving object and a planet that happened to be watching at exactly the right moment in exactly the right direction. Most of the time, across most of the galaxy's history, no one is watching. Objects like Oumuamua have almost certainly passed through this solar system before, uncounted times, long before any species on Earth possessed the instruments or the curiosity to notice. This time, someone did. That, more than the mystery, more than the debate, more than the unanswered question of exactly what pushed it slightly off its expected course, may be the most remarkable part of this entire story. Not that Oumuamua passed through. Objects like it likely pass through fairly often on the timescale of a galaxy. But that for once, in the narrow fleeting window when it happened to be close enough and bright enough to see, there was, finally, something here capable of looking back. There is a quieter thread running through all of this, worth mentioning before this story closes for the night. The kind of discovery that first identified Oumuamua, a single anomalous data point buried within an enormous stream of routine survey images, no longer depends entirely on professional astronomers manually scanning frame after frame by eye. Modern sky surveys, including the Rubin Observatory's ongoing legacy survey, generate millions of individual detection alerts every night, far more than any human team could review directly. Increasingly, these alert streams are made available in close to real time to a broader network of researchers, smaller observatories, and in some cases, carefully vetted amateur astronomers, whose rapid follow-up observations often provide crucial additional data points during exactly the kind of narrow closing window that made Oumuamua's own confirmation such a race against time. Gennady Borisov, the discoverer of the second interstellar object, was not employed by any major observatory or research institution. He was an engineer who built his own telescope, ground his own mirror, and spent his personal time methodically searching the sky, exactly the kind of dedicated, independent observation that the field continues to depend on, alongside its largest and most expensive instruments. This is not a call to go outside and search the sky personally, though for anyone curious enough to try, dedicated communities of amateur observers do exist, sharing data and techniques openly. It is, instead, simply a reminder that this entire field, however advanced its telescopes and however sophisticated its statistical models have become, still rests, in part, on the same basic human habit that made Oumuamua's discovery possible in the first place. Someone, somewhere, taking the time to look carefully at the sky and to notice when something in it does not quite match what was expected. That habit is, in its own quiet way, very old. Older than telescopes, older than written astronomy. As old as the first person who looked up at a clear night sky and wondered, without any expectation of an answer, what exactly they were looking at. Oumuamua never answered that question completely, neither did Borisov, not entirely. Even 3I/Atlas, studied more thoroughly than either of its predecessors, still leaves portions of its own story only partially resolved. That incompleteness is not a flaw in the science. It is simply an honest description of where the science currently stands. One visitor, one brief window, one careful measurement at a time. Only a number, 11 days. 11 days, set against a journey that has already lasted, by conservative estimate, hundreds of thousands of years, and will likely last millions more. 11 days, during which an object that predates human civilization by a margin too large to comfortably picture, briefly reflected sunlight toward a handful of telescopes on a small, warm planet, and then moved on. Consider, one last time, the scale this single encounter sits inside. Our galaxy alone contains somewhere between 100 and 400 billion stars, each one, in all likelihood, once surrounded by its own disk of gas and dust, each one capable, during its own early chaotic period of planet formation, of ejecting its own share of leftover debris outward into the space between stars. If even a small fraction of those stars produced objects even remotely similar to Oumuamua, the total number scattered across the galaxy right now, at this very moment, tumbling silently between one star system and another, would be almost impossible to write down in full, a number stretching well beyond anything encountered in ordinary daily life. Almost all of those objects will never be seen. They are too small, too faint, too far from any star capable of illuminating them, too far from any telescope capable of catching that faint illumination, even if it existed. Oumuamua was not special because it was rare, in the strict sense. Objects like it are likely common, on the scale of an entire galaxy. It was special because, for 11 days, the immense indifferent statistics of a galaxy containing hundreds of billions of stars happened to align, briefly, with a single planet whose inhabitants had, just barely, finished building the tools required to notice. That alignment will not happen again with this particular object. It is moving outward, permanently, and it will not return. But the statistics that produced it have not changed. Somewhere out there, right now, another object very much like it is almost certainly already in motion, following its own long, patient arc toward whatever narrow window might someday bring it close enough to be seen. Perhaps that window arrives in a year, perhaps in a decade, perhaps not within the lifetime of anyone listening to this story tonight. Either way, the watching continues, quietly, patiently, one clear night at a time. There will be others. 3i/Atlas has already shown that the wait between visitors may be shorter than anyone once assumed, and the Rubin Observatory's cameras are, even now, scanning the sky nightly, watching for the next one. But tonight, this one is enough. Somewhere out there, in the direction of a constellation most people will never learn to find, a quiet, tumbling fragment of another star system is still moving. Still red, still cold, still alone, still real. If tonight's story helped you drift towards sleep, a subscribe and a like go a long way, and turning on notifications means you will not miss the next one whenever it finds its way to this channel. Everything you heard tonight is real. Oumuamua is out there right now. Good night and sleep well.